When a phone or modem attaches to a 5G network, the network does not only ask, "Who are you?" It also asks, "Is this device allowed to be here?" That second question is where the Equipment Identity Register, or EIR, comes in. In the 5G core, the EIR is the service that checks a device's physical equipment identity, the PEI, and decides whether that device is allowed, suspicious, or blocked. The page we are studying shows two related paths. One is the equipment identity check itself, AMF to EIR and back. The other is service discovery for that EIR function in the 5G service-based architecture. AMF may first find the right service through the NRF, and in some deployments even through a global NRF. So this is not just a single API call. It is a small control plane journey. Keep two identifiers in mind. The SUPI is the subscriber identity, tied to the customer or SIM profile. The PEI is the equipment identity, tied to the hardware, often the IMEISV. The network may want both because a subscription can be valid while the device itself is still on a blacklist. In the next scenes, we will unpack the route, the request, and the response so the diagram becomes a story instead of a wall of boxes and arrows. Let's separate the two identities that appear in this example. First, the subscriber. In 5G, the SUPI identifies the user or subscription. In the request shown on the page, it appears as an IMSI style value. That tells the network which subscriber profile is involved. Second, the device itself. The PEI, or Permanent Equipment Identity, is the hardware identity of the terminal. In practice, the example uses an IMEISV value, which is the IMEI plus software version. This matters because the network may trust a subscriber but still reject a particular device if it has been reported stolen, cloned, or otherwise barred. So the EIR is not a replacement for authentication. It is an extra safety check. Think of it as a gate that sits beside normal registration. The AMF can accept a registration request, but before the session is fully trusted, it can invoke the Equipment Identity Check service. This design is especially useful in large operator networks because policy about devices is often shared across many regions and systems. That is why the page also shows NRF discovery and even a global NRF forwarding step if needed. The network is trying to find the right service instance before it asks the actual blacklist question. Now let's follow the discovery path drawn at the top of the page. The notation says EIR discovery goes from AMF to NRF, then to NRF global if necessary, then back through NRF to AMF. That means the AMF does not need to hard code the exact EIR instance. Instead, it asks the service registry where the function lives. This is a classic 5G service-based architecture idea. Network functions expose services, and other functions discover them dynamically. In the picture, the EIR is part of the wider 5G core service mesh, alongside NRF, UDM, AUSF, SMF, PCF, and the rest. Only a small slice matters for this identity check, but the architecture lets that slice be located flexibly. The source also notes an implementation detail. EIR discovery is not supported at the current software level. That is a reminder that diagrams often show the intended architecture, while a deployed system may support only a subset of the flow. In other words, the arrows explain both the ideal design and the real operational dependency. Once discovery succeeds, the AMF can invoke the actual equipment identity check service. That service is provided by the 5G EIR, and its job is simple: evaluate the PEI and return whether the device is blacklisted or allowed. The page gives us the concrete API shape. The AMF sends an HTTP2 GET request to the EIR endpoint, /n5g-e-EIR-EIC/v1/equipment-status. The query includes the PEI and the SUPI. So the request is saying, in effect, here is the device, here is the subscriber, now tell me the equipment status. That pairing is important. The PEI alone tells you which device is under inspection, but the SUPI gives context about the registration attempt. Operators can use that context for auditing, correlation, and policy decisions. The service then answers with an HTTP 2200 OK and a small JSON body containing a status field. In the example on the page, the status is whitelisted. That means the equipment is considered acceptable. If the status were blacklisted, the downstream registration logic could respond differently, such as denying access or triggering an investigation path. So the response is tiny, but the consequence is large. A one-word status can influence whether a device is allowed to continue attaching to the network. That is why this check belongs in the control plane rather than in the data plane. It is policy, not payload. It helps to think of the EIR as a decision point in a registration pipeline. The AMF first receives the registration request from the device through the GNB. Then it may run identity-related checks, including this equipment identity check, before the device is fully accepted into service. If the EIR returns whitelisted, the AMF can continue the normal registration flow. If the EIR returns a blacklist result, the network can stop the process, reject the attempt, or apply a stricter policy depending on operator configuration. The page does not show every branch in that policy tree, but the point is clear. The EIR is a screening function. This is why the request includes both device and subscriber identifiers. It lets the operator tie the event to a specific handset, a specific SIM, and a specific control plane transaction. That is useful for security, fraud handling, and troubleshooting. Notice also the placement of EIR in the broader service map. It sits among other 5G core functions, but its role is very narrow: device trust. That narrow role is exactly what makes it easy to miss in a huge diagram, and exactly what makes it worth isolating and studying carefully. Let's finish by reading the diagram as one story. A device starts a registration request through the GNB. The AMF receives it, and then the AMF may discover and invoke the EIR service. The service checks the equipment identity, the PEI or IMEISV, and returns a status such as WHITELISTED. The big lesson is that 5G registration is not only about network location and subscriber authentication. It can also include device reputation. The diagram on the page captures that idea in 2 steps. Step 6 for registration request and Step 7 for equipment identity check. Those 2 steps sit inside a much larger 5G core, but they are enough to show how identity, discovery, and policy connect. If you remember only one thing, remember this. SUPI says who the subscriber is. PEI says which device is trying to attach, and EIR tells the network whether that device should be trusted. That separation is a core design pattern in secure mobile systems. So when you see a dense 5G core diagram, look for the flow of questions. Who is the user? What is the device? Where is the right service? And what policy result comes back? That is the logic behind the arrows here. Before we close, here is a practical way to read a dense 5G core diagram like this one. Start by finding the event that triggered the page. Here it is the registration request from the device through the GNB. Then locate the control function that first receives it, the AMF. After that, look for any service discovery step, because in a service-based core, the AMF may not know the exact destination ahead of time. Next, identify the special purpose function being queried. In this page, that is the EIR. Ask what that function is responsible for and what input it needs. The answer is simple. it checks the PEI, often the IMEISV, and returns a status. Finally, look at the result and ask how the rest of the system would react. If the status is WHITELISTED, registration can continue. If not, the network can block or restrict access. This reading strategy works beyond the EIR. In any 5G core diagram, try to separate transport, discovery, policy, and decision. Transport is how the message moves. Discovery is how the network finds the service. Policy is the rule being applied. Decision is the actual response. If you can classify each arrow into one of those buckets, the diagram becomes much easier to understand. So even though the page is crowded with boxes, the logic is actually compact. A device asks to join. The AMF verifies identity and discovers the right service. The EIR judges the device, and the network proceeds based on that judgment.